Well, many thanks to people for participating. It's actually almost community-like to see that lineup of people. I'd almost rather have a conversation with everybody than talk about big history. And I wasn't going to say this, but it struck me that it's worthwhile to note. I have a half-mile driveway, and I have a small John Deere tractor, and it currently is stuck in the driveway. It won't start, and I feel, tension about that, and I'm not quite sure how I'm going to get it running. And the interesting thing is, so I want to relate it to life on the planet, to the fact that we all have these individual lives and we all have these dramas that are constantly unfolding, and they pull our energy and our attention away from this bigger story, which can be told in innumerable ways. It could be told as a religious story, a spiritual story, a science story. Big history, is pretty much science, but I think it can give us goosebumps. And we have these two lives I think we need to live. I need to get my tractor started. But I need to retain some level of awareness that I'm alive on this planet. And it's not all about this individual drama. I don't know where and when I haven't entered here early. So I think I want to reiterate, I think I may have said it all the other two times. There's a lot of information, and this is, I thought, when I looked at it over the last half hour, I thought, oh my gosh, this is a little bit too much science. It's good and it's interesting, but this is not material that can be remembered. And I think the best possible outcome is enhanced awareness in any way. And I have a quote written down. I didn't write it down, actually, a bit of it to remind me, but Thich Nhat Hanh, I think most of you know who Thich Nhat Hanh is. He's a Vietnamese monk. And in fact, I think he's probably dying. I heard that he had a stroke 3 or 4 years ago, and he's not been well. And I heard that he stopped eating 2 weeks ago, but he's not died, or we would hear about it. I would hear about it. Anyhow, he's exemplary. And he said, it's just, I think one of my favorite passages of his is, people say that it's a miracle to walk on water or to walk on air. Yeah, I say it's a miracle to walk on the earth. And, that's what I want to be able to remember while I all uptight about my tractor being broken down. And I was trying to talk to myself about that earlier today. So let's see, we have talked about, we have 4 programs for this big history presentation. And the first was trying to get the universe established and elements and planets. And the last one was pretty much on geology. And now we want to get life established on the planet, because that's the big history journey. That's the big history story. There was no life. There may be no life in the whole rest of the universe. We never found any. And it's rather inexplicable. Nobody knows where life came from. And as we'll see as we go through this, it appears that life only appeared once on the planet, and because chemically and genetically it all uses the same chemicals, and it appears that all life is related, that all life has diverged from one original occurrence of life, and we do not know how that life came about. There have been many ideas about how life came about, and one good one is spontaneous combustion, which actually at this point isn't that far-fetched as it sounds, but there is if you want to, you can create life in this way. And this may have been a recipe from Aristotle. If you take a small pile of rags and add some grain, within 4 days, it'll turn into mice. Mice will be in those rags. They'll just appear from nowhere. Spontaneous combustion. And it was, Aristotle thought that swallows just appeared magically out of ponds, because for months at a time there were no birds, there were no swallows on the pond, and then on an early day in April, there would be 100 swallows over the pond. And he thought they had just appeared out of the pond. And that's an interesting reflection on the human condition, because they didn't know about migration, didn't know how big the world was, didn't know that swallows had any place to go. It's been a journey to what little we know about life. It's been a challenge to learn what we do know. So I mentioned this quote before. It's become a favorite by Christian Duve, a Nobel Prize winner in medicine. He said, life may be an obligatory manifestation of matter, bound to arise wherever conditions are appropriate. And that fits with the little conversation we have had about the built-in electrochemical attraction that atoms have for one another. Where did that come from? Who? Nobody knows. Nobody knows where that came from. But atoms, they want their shells filled, and they will just automatically join, and the complexity builds over time. And that then becomes, I think, that is one of the themes of big history. So big history has come up with a way to try and tell this very difficult story, and they've broken it down into some categories that they call themes. And one of the themes is increasing complexity, and we'll talk a bit about that in the next slide. But life started with hydrogen, and as I like to say, look around, there's a lot going on. It all has emerged over time. Emergence is a second theme of big history, and it is certainly one of the most hopeful aspects, if we're troubled by the human condition. The journey of life is an emergent journey, and new things are emerging from old, and it's not predictable. Goldilocks conditions, there are many aspects, mysterious aspects, we talked a little bit about it, that are just right for life. And then life, the journey, the evolutionary journey passes notable thresholds. The first one is the appearance of the universe, the Big Bang. As I like to say, Brian Swim, who's a cosmologist, says, well, that's impressive. Everything appeared from nothing. Nobody can explain that. Stars, there were no stars in the first few seconds. I don't know how long, probably longer than seconds, but there were no stars. Stars appeared when hydrogen was pulled together by gravity into very dense masses that start smashing into one another and ignited. That is a threshold. There were no stars, then there were stars. There were no planets. There was no life. It's not over. It's never over. So it's interesting to contemplate that indeed there are thresholds. We can recognize them. I think I don't have it in this. I showed it once before, but I came up with some different thresholds than David Christian. David Christian is Mr. Big History. He coined the term. He's a wonderful educator on big history, but he didn't include photosynthesis. I don't know how you could do without photosynthesis, and we will talk a little more about photosynthesis. Emergence, well, so we started with hydrogen, and now we have blue whales. Hydrogen is the smallest atom. Single atom has one proton, one electron, often doesn't have even a neutron. I don't know why. Blue whales are made up of 100 quadrillion cells, and each cell can have 100 trillion atoms. And I'm just illustrating the fact that complexity is one of the themes of big history. This is the largest organism that's ever lived, and nothing like this probably could live on land. 100 tons, 200,000 pounds, but it's supported by, the heavier medium of water, and does live in there. They've been threatened with endangerment, blue whales, and all large organisms are threatened because of the impact of Homo sapiens, which we touch on briefly at the end of this program and go into more, not the environmental effects of Homo sapiens, but the evolution of Homo sapiens in next week's program, which is also a great story, really so fascinating, and has been meticulously unearthed, by the scientific community. They had to dig up bones that were 300 million years old, and you had to ferret them out with a paintbrush. So, as I said, all life has evolved from single cells, and you can see here that Homo sapiens evolved from a single cell. This is a cartoon. I think it's very cute. When we were a single cell, we did not look like a person. Carrots did not begin. But it is a fact that not only did life first appear as a single cell, all the scientific evidence points in that direction, but it was us one single cell, and all life evolved from that single cell, so all life is related. So we showed this last week. This is a reminder of what the human concept for the diversification of life at this time is, and that is that there are 6 kingdoms, and those are the 6 kingdoms, starting with tiny cells, archaea and bacteria, and then larger cells and larger multicellular organisms up on top there. Protists on the left tend to be single-celled, but brown algae are protists, and those, remember the brown algae that washes up? What do we call that? I forget. Sea kelp. Those huge whips that wash up on the shore. That's a protist, one of some of the biggest organisms on the planet. So down at the bottom it says last universal common ancestor, LUCA. It's fun to call that. That's the origin of life, and the evidence is that all these organisms are created. Now, there's one other major division. I'm going to pull it up here, and that is that these organisms have different kinds of cells. Bacteria and archaea have a type of cell called prokaryotic cells. And the upper organisms have a different kind of cell. They're larger cells. They're called eukaryotic cells. Interestingly enough, prokaryote means before the cell or before the seed. Don't forget these names were made by Homo sapiens, which we gave ourselves the name wise human, Homo sapiens. We called our cells eukaryotic cells, which means true cells. So it's a stroke of good fortune that we got the true cells and bacteria got fake cells. I'm kidding, but that's what those words mean. We gave ourselves the true cells. They're very different, and I forget exactly where it comes up, but we talk about prokaryotes and eukaryotes soon in this slideshow. This is the same. This is the same as this, but it's a more complex image, just to show that the actual complexity is tremendous of the family shrub of life. Now, we like to call it a family tree, but it's so branching that the evolutionists will say, you should call it a shrub because it's just branched and branched and branched. I put LUCA in here in the middle there, LUCA, last universal common ancestor. I just was noticing that below the colored part, it has the, there have been these extinctions. It says mass extinction, mass extinction, mass extinction. And there's little holes made in the places where the shrub is colored. And that's an interesting phenomenon insofar as it's been controversial and mildly traumatic to understand the nature of the evolution of life and the evolution of geology. Has it been slow and steady and uniform, or has it been catastrophic? Are there major catastrophes? And because of the nature of religion, I would say at this moment, I'm thinking especially of Christianity, and the nature of the human mind, we wanted the universe to be orderly. Of course, we want it to be safe. We don't want catastrophes. And so when scientists, scientifically oriented people, started finding fossils of huge animals that no longer existed, people could not believe that something like that could be extinct. And an interesting anecdote about that is when Thomas Jefferson commissioned Lewis and Clark to go to explore the western United States they left, I think, in 1804, 2 years out there, he thought they might find dinosaurs. And certainly they might find mastodons. They had figured out that these big elephants had lived in America and they were not around, and nobody wanted to believe that life would go extinct. And the interesting thing is, which is it? Is it uniform or is it catastrophic? And the answer to these questions are always, it's both. That there's this tremendous uniformity in the evolutionary progress of life, And there have been massive, massive catastrophes where the Permian extinction 250 million years ago, you could find that on there. It's thought to have killed 90% of all life on the planet. And there have been many mass extinctions. It's both. So what is life? We're moving into life here. This is a hard assignment, actually. Man, I don't know what I would have put down. I got most of this, from life self-assembles. It puts itself together. There's no outside force putting it together. I mean, humans start out as a single cell. The sperm and egg unite into a single cell, and all the information on how to grow into an adult human being is in that single cell. It self-assembles. Well, granite self-assembles too, by the way. So it's not, that won't cover the full definition of life. Life is sentient. It responds to the environment. It doesn't necessarily mean it's intelligent. In fact, it'd be like, what do you think of human intelligence? Well, it would be a good idea. I mean, we're still waiting for intelligence, but all life is sentient. All life responds to its environment. Single cell bacteria move towards light, away from light, towards food, away from light, away from food. It's sentient. And this one is, to me, quite interesting. All life acquires energy to maintain an internal environment that's out of equilibrium with the external environment. I like that a lot. Life is out of equilibrium with the environment. It just means that, we are semi-permeable membrane and we take in what we want. I showed that quantity of carbon. The quantity of carbon in the Earth's crust was almost nothing. It was like 1/10,000th of a percent. In a human body, it's like 45%. Totally out of equilibrium with the environment. And that's true for all the elements that make up the human body. It takes energy to maintain that internal environment different from the outside. And so we have to acquire energy. And all living things do that, made of cells. Don't think of that, but there are no living organisms that aren't made of cells. And that leaves out viruses, which I mentioned at the end of this program, which are not really cells, but are they alive or are they not alive? It's argued by the scientific community, and life reproduces. I think because the geosphere, the Earth, is dangerous. It's hard on living organisms. The energy waves damage living cells over time, and we need to start again. And life adapts because the physical environment is constantly changing. We don't think of it in that way. We're aware of the seasons, but are we aware there was a mile of ice in the Methow Valley only 16,000 years ago? And it happened many times. It melted. Life had to reestablish. The temperature changes. Rivers come and go. Life has to adapt to those changes. So this is about cells. Cells have an external membrane, and they let in their friends and they leave out their enemies. And it's interesting parallel with human society, and especially, it's not quite as evident now. We can't build a wall around the United States, although we can build one along the southern border. And I think we need one on the northern border because the Canadians keep stealing my hockey pucks. But in earlier civilizations, they built walls, which is very much like a cell, to maintain a different internal environment. And then I added this because it's the same thing. This is a concrete wall in Bethlehem to keep the good guys in and the bad guys out. And, we don't need to, who built that wall. And Banksy, some of you have heard of the artist Banksy, painted this picture of two angels prying the wall apart. Because something there is that doesn't love a wall, as Robert Frost said. And over time, the walls go down. So these two angels, see, they made this crack. He's got a crowbar. It's a great painting. It's in Bethlehem, of all places, in Bethlehem. So there are scientists who note then that the atmosphere of the Earth is a semi-permeable membrane. I mean, it was Richard Lewis. Is that his name? Oh, Lewis Thomas, I think. He wrote The Lives of a Cell. He said, when I think of the Earth, it appears to very much to be like a cell. The atmosphere is a semi-permeable membrane. that keeps out the enemies, the dangerous aspects of the universe. The temperature of space is 455 degrees below 0 Fahrenheit. Temperature of the Earth, the average temperature of the Earth is about 50 degrees, and it's because we have the semi-permeable membrane. So it's just a very interesting phenomenon. Moving on to life itself. So we have these two types of cells, and we're going to differentiate between them. Prokaryotes, I've mentioned, prokaryotes and eukaryotes. All of our cells in our body are eukaryotic cells. They're eukaryotes. They're much larger than prokaryotic cells, which means they're much larger than bacterial cells, much larger than Archaea cells, and very different. Our cells are complex. They're 100 times larger, and they have organelles inside. If this is a simplified drawing, but this is a bacterial cell, prokaryote. There's no nucleus. There's just an external membrane. There's no nucleus. There's no organelles. There's just cytoplasm and DNA. That's all there is in a eukaryotic cell. When they reproduce, they just split in half. There's no sexual reproduction per se. There's no recombination with a separate organism to reproduce in prokaryotic cells. Major difference from eukaryotic cells. But there is vast room for genetic variation in prokaryotes in this way. And they call it informal sex. When a bacterial cell, a prokaryotic cell dies, cell wall disintegrates, and the DNA goes into the surrounding environment, whether it's water or cytoplasm, probably not the air, but something liquid, floats around, and other prokaryotic cells can pick up fragments of that DNA and incorporate it into their DNA structure, and you get a new organism. And it happens all the time. I think maybe in the next slide we see that this is the reproductive rate of prokaryotic cells. They can reproduce every 20 minutes by splitting in half. So that, you get the progression there, 40 minutes, 60 minutes. So in 10 hours, 1 billion cells. I have this tidbit of information that says if this progressed for any initial cell for 3 days, that colony of cells would weigh more than the Earth itself. That doesn't happen because it's competitive. And these prokaryotic cells are constantly fed on by other organisms and non-organisms. I've been very interested to learn that one of the primary sources of energy or prey for viruses are bacteria. Bacteria keep this bacterial growth in check. So I pass that on because, at the moment, we pretty much demonized viruses, but cannot live without viruses. Well, that comes up again later. This is the location of bacteria on our skin. We have approximately 1 trillion bacteria living on our skin. And the real point here is ecology, that even our bodies are a community of life vastly greater than we ever knew or could imagine. So 1 trillion bacteria on our skin, and these are different kinds of bacteria. I didn't bother looking them up. And it doesn't matter where they are, except for the shock factor, that we have bacteria all over our skin. That's 1 trillion. We don't know for sure, but 30 or 40 trillion inside of our body. We have more bacterial cells than we have human cells. Nobody knows for sure how many, but the current estimate is, I said 30 or 40, I would go to 50. I think it's about 50. So something that was amusing to me here, and I did circle it down at the bottom, it says cyanobacteria. That's the light purple. I had to track it down with those little pie charts. Cyanobacteria are photosynthetic bacteria. Cyanobacteria are like plants. They make their own food. So we have what looks to me like cyanobacteria in our upper sternum. Let's see if here's my cursor, if you can see it. Upper sternum, and that looks like the light purple. And in our ears. So there's hope that in the future we'll be colonized by more cyanobacteria and we can make our own food in our ears and we won't have to eat anymore. It's just a joke. But cyanobacteria is there. They are photosynthetic. That's no joke. But so as with viruses, we're terrified of bacteria. I don't know, Andy, are you there? I can't see you. Andy's a retired physician. And we've talked a little bit about these sanitizers. And so he, in masks, and he did a lot of operations and constant sanitizing and constant operations. But you're killing, when you use these hand sanitizers, you're killing all the beneficial bacteria and viruses on your hands. They are not all inimicil. Interestingly enough, so anaerobes, Archaea, the group of prokaryotes that are not bacteria, they're called Archaea. They're all anaerobes, which means they don't use oxygen to get at their energy. But there are no harmful Archaea known. I thought that was fascinating. They're all either neutral or beneficial. They're probably not on your hands because your hands are in the atmosphere, but they are in your stomach and in your intestines, Archaea, as with bacteria. Anyhow, mostly it's acute drawing. And it's worth noting that. So the word I have is, we have about 40 trillion human cells, 50 trillion bacterial cells, and 400 trillion virus particles in our bodies. And it's just the way it goes. We are a community of life. So I just mentioned this. Archaea, many bacteria, they're anaerobes. They existed. There was no oxygen in the atmosphere for the first 2 billion years. There was life, but there was no oxygen. Life lived without oxygen. Archaea, the word means ancient. They probably were the first organisms on the planet. They function without oxygen. Fortunately, we don't need to go into that. Photosynthesis didn't exist. It was invented by cyanobacteria. They used to be known as blue-green algae, but they're not algae. Cyano means blue. So photosynthesis, it's worth dwelling on. I made it one of the thresholds of life. And so what I have, I would like to find, and I know that I highlighted it here because if you look at the information on so many of life's processes, there's a life process and there's leftover material, and it'll say it's given off as a waste product. So in photosynthesis, carbon dioxide is taken in, water comes up from the roots, it's made sugar, and oxygen is given off as a waste product. So I started looking that up, and there was an article in the last Naturalist, Where Does Nature Put Its Garbage? And this is where I got that from, that article. It says BBC, on a BBC page on photosynthesis, it says carbon dioxide is a waste product of anaerobic respiration, and oxygen is a waste product of photosynthesis. And I have other quotes. Waste product. Oxygen is a waste product. So there is 1.2 billion metric tons of oxygen in the atmosphere. And as I said in that article, that is a lot of garbage. What are we going to do with all that garbage? But well, it's not quite where I thought. But this is some of the thought to be some of the earliest photosynthetic organisms. That's actually a rock called a stromatolite, but it's a rock that has been made by cyanobacteria, which are photosynthetic bacteria, live in shallow water. That's tidal there, so they're underwater a lot of the time. Early life needed that because there was no I forget the name of it at the moment. The protective layer of three atoms of oxygen. You can't tell me because you're all muted. In the upper atmosphere that blocks cosmic radiation. You could not have life on land. The cosmic radiation was far too powerful. What was that?
Ozone?
Yeah, the ozone layer.
Ozone?
Thank you. Yeah, the ozone layer. The ozone layer is critical to life. It's O3. It's 3 atoms of oxygen combined together, and it blocks the most damaging high energy rays that would rip our DNA to pieces. There was no ozone in the early atmosphere, so life originated in water. The water served as that ozone layer and blocked the damaging aspects, the entry of cosmic radiation. So the stromatolites lived in shallow water because life was possible there. They're photosynthesizers, but they also accumulate mineral particles, basically sand, probably to protect themselves from high energy rays coming in from the atmosphere, and they build up over time into these structures. There are there are a lot of these stromatolites, fossil stromatolites, all over the world. Interestingly enough, they still exist, but only in a couple places. This is in Sharks Bay in Australia, and apparently they're in the Bahamas, and I don't know if they exist anywhere else. It's just an example of early life, and how life, not how life originated, but how it existed in the early days. Well, these are photosynthetic organisms. They're giving off oxygen. As I've said before, oxygen is a very reactive element, one of the most reactive elements, which just means it wants to react with other elements. It wants to fill that second shell. It only has 6 electrons and it wants 8. So now the atmosphere, the red line there, 21%. The atmosphere now is 21%. It would be 0 without photosynthesis because oxygen is so reactive. Now, interestingly, the evidence is that oxygen went up 400 million years ago to above 30%. And that's when, if you've heard about insects, there were dragonflies that were a foot long because there was so much oxygen that insects that didn't have lungs, they didn't pump the oxygen like we do, it just had to diffuse in through holes in their exoskeleton, could get bigger because it could access more oxygen. An interesting thing is, I don't know how you would put fires out when the oxygen was above 30%, because all a fire needs is oxygen. Once it started, everything would burn. I don't know how that works, but it's fascinating that. So life is constantly pumping oxygen into the atmosphere. In fact, oxygen levels drop slightly in the northern hemisphere in the winter because there's no photosynthesis in the winter. These are called banded iron formations. This particular one is in Australia, but they're all over the planet. BIF for short, banded iron formation. This is iron that combined with oxygen, it reacted with oxygen, it rusted basically, made iron oxide and turned into a solid. This was in water, in the oceans. There was iron in solution in the oceans. But when the ocean started to increase in oxygen, which had to happen before the atmosphere did, the iron reacted with the oxygen, turned into a solid, and precipitated down into the sediments. It created these banded iron formations, which are the major iron deposits for human access to iron on the planet, banded iron formations. It's a geological formation that is a product of life because it occurred because the atmosphere was starting, and the oceans first, filling with oxygen. They're always in these strata. I looked it up and I could not find, and I could not remember. See, it alternates with quartz, I believe. Those light, the red is the iron. I believe the white is silicon dioxide, quartz. There's some explanation. It could be seasonal. That's an interesting phenomenon. You can find it online. So photosynthesis. Photosynthesis drives the energy of the planet. So I mentioned cells are out of equilibrium with their environment. They need energy. They need energy to pump out the stuff they don't want and maintain their cell walls and allow in what they want. What's the energy source? It's the sun via photosynthesis. And what is happening is that photosynthesis is turning the earth into a battery. It's pumping the positively charged elements, not quite accurate, oxygen into the atmosphere, and the more negative elements, which is the product of photosynthesis, sugar, starch, and beyond that, cellulose, it's on the ground. The sugars want to react with the oxygen. There would be no reason for photosynthesis if it wasn't setting up this battery. You would just build organic matter. There would be no way to break it down. You would run out of the elements necessary for life, and life would grind to a halt. What I'm saying is oxygen is not a waste product. It's integral to the functioning of life. So oxygen in the atmosphere, hydrocarbon on Earth, it's created this battery situation. And So what we get then, here's the process of photosynthesis. You know, it's carbon dioxide. So here's my cursor. Carbon dioxide, CO2. It doesn't combine with water. It takes these two little electrons. It splits. The energy of the sun splits these two electrons, the two off the water, transfers them to the carbon dioxide, and here they are, hydrogen. They've made sugar. This is a carbon ring. It's carbon 6, this ring. They represent it as a ring, but this is sugar. And the oxygen is released into the atmosphere, but the oxygen wants these hydrogen atoms back. It's hungry. It was only the energy of the sun that made this possible, and so the oxygen is hunting for hydrogen. And so, well, that came up by itself. So this is the process. They call it respiration. We think of that as breathing, but that's getting the oxygen into the cell. They call it cellular respiration. Here we have, over here, we have the sugar molecule that was made up above, combining with oxygen in one way or another. It needs a catalyst to access these, you know, enzymes in our body. And we get back what we started with, carbon dioxide and hydrogen. And here's the energy of the sun that started up here and was captured in this carbohydrate bond here. It's now been broken, and it's the energy for a cell, many cells, for the 40 trillion cells in your body to maintain disequilibrium with the environment. And, you know, they call energy as the ability to do work. It can also be defined as the ability to have fun. But down here is something else. What's happening here? This is the exact same thing. Here's the sugar. It's combining with oxygen, releasing carbon dioxide and energy. What is this? This is fire. Fire is the exact same thing as cellular respiration that occurs in your stomach, which is why we encourage people not to eat your food too fast. You might burst into flame. It's a joke. So eukaryotes, remember prokaryotes and eukaryotes. Eukaryotes are 10 to 100 times larger. Eukaryotes have little cells inside the big cells. It's particularly mitochondria. And we have like 2,000 little organelles inside each cell. How did such a thing occur? And this is, you know, fairly recent information. I mean, the last 20, 30 years, it appears that it occurred when one prokaryote tried to engulf and consume another prokaryote, which is what they do all the time, and failed to digest it. And they began to work together. How that happened, we don't know. But the evidence for this is that these multitude of mitochondria that we have in our cells, I don't know if it's the next slide, it is, they have their own DNA. We have up to 2,000 mitochondria in many cells in our body, not every cell. They have their own DNA separate from the DNA in the nucleus of each one of those cells. And the DNA is passed on only from the mother, which means, so I put that, another little joke, hope you got along with your mother, because you actually have more of your mother in your body because of this phenomenon, not by much, a thimbleful, more of your mother than of your father, because all the DNA in your mitochondria, which you have billions of in your cells total, came from your mother and your mother's line. So it's interesting to think that everything in terms of your father's line is not included in the mitochondria. And this is the evidence that mitochondria were once free living cells that now live inside of larger cells. Here's a little size of prokaryotic compared to eukaryotic, and a sense of the difference in complexity. Remember that increase in complexity is one of the themes of the evolutionary journey, and here you have it in a nutshell. Prokaryotes, they don't have a nucleus, they don't have organelles, they don't have much, but they do have DNA. They have a cellular membrane so they can maintain a separate internal environment, no mitochondria, and I'm not sure what all that other stuff is. Golgi bodies, maybe no Golgi bodies, I'm not sure, but eukaryotic cell up to 100 times larger, has a nucleus, DNA within the nucleus. So there were no eukaryotic cells. I had to put in eukaryotes here. There they are. I made it appear and disappear on this chart. So the solar system formed 4.5 billion years ago. Planet formed in this area. oceans. Life, here's first life. There is evidence for life at about 3.8 billion years. It's, it's not life itself. It's vague chemical evidence in ancient rocks. That's what it is. That's how, clever human beings are to be able to decipher that. So these larger cells appeared halfway through the evolutionary journey on the planet, and coincident with the increase of oxygen in the atmosphere after cyanobacteria started to pump oxygen into the atmosphere, because these larger cells need more oxygen. Especially you start forming multicellular organisms that are not in immediate contact with the atmosphere, and somehow that oxygen has to be transported via some kind of circulation system. Couldn't happen until the oxygen levels increased. So life made larger life possible. It's an emergent property of life on Earth. And we got up to dinosaurs. The world filled up with dinosaurs, and apparently we're wiped out by a catastrophe. An asteroid strike 6 million years ago. There's strong evidence for it. So we looked at this last week. I love this chart because it's such a shock. We just don't think of continents as growing, but indeed the evidence is continents grew over time. And I mentioned last week, there's evidence that there was a spurt of growth about 2 billion years ago. What was happening 2 billion years ago? The atmosphere was filling up with oxygen. There is a connection between the growth of continents, which are like 45%, continental rock, high silica rock. Silica is 45% oxygen. It's made out of oxygen. I mentioned last week, I couldn't quite remember. There's a connection between the growth of continental rock and life. Life put the oxygen in the atmosphere. Cosmic radiation splits water. When water is a water vapor in the atmosphere, the radiation causes high energy radiation can split it. So now it's oxygen, hydrogen. Hydrogen is so light with only one proton that it's not firmly bound by gravity, and hydrogen can and does escape the Earth's gravity. It's quite possible we would have lost some or all of our water through this process, except the atmosphere is now full of oxygen because of life, and the oxygen reacts with that hydrogen, makes water vapor, drops back down to the Earth. So it's likely that life helped retain the water on the planet. Continents, the process of making continental rock, we talked about a little bit last week, involves the presence of water. And there is, if anybody wants to look into it, you can Google granite, a planetary response to liquid water, and you'll get a study on that. Granite, a planetary response to liquid water. That's what we're talking about. No water, no granite. No life, no water. So here's a couple little organisms, prokaryotes and eukaryotes. Cyanobacteria, it's possible that upper right is cyanobacteria. Looks a little green, they should be bluer. But the other ones are diatoms. So diatoms are eukaryotic cells. They're larger cells. We've heard of diatoms, but diatoms don't get the credit they need because they produce 25%. They're photosynthetic organisms. Diatoms are photosynthetic organisms that pump oxygen in the atmosphere, and it's now thought they're responsible for 25% of the oxygen in the atmosphere. And some of these diatoms are very common in the Meha River. If you look at the slime on the rocks in the river, it's full of diatoms, completely full of diatoms. And diatoms make their shells out of silica glass. Very beautiful creature. So we've been on this journey where life appeared. We don't know how. Prokaryotes, bacteria, and archaea were the only organisms for 2 billion years. It appears that eukaryotes appeared from some sort of symbiotic interaction between two prokaryotes. And as the atmosphere filled up with oxygen, you could get multicellular organisms. The plant kingdom began to emerge. And really now, if you look at the plant kingdom, so these are just nice pictures of a few creatures in the plant kingdom, but the most interesting one actually, and I hadn't fully thought about this, in the upper left, that is an algae. I forget which one that is, but it's a green algae. Green algae is now included in the plant kingdom. The other algae aren't. Red algae, sorry, not coming. Brown algae, no. And diatoms are brown algae, and they're protists. It didn't used to be. I mean, even when I went to school, algae was not. Green algae was, but now they're so closely related to plants. It's thought that the plants evolved from these green algae. They're included in the plant kingdom. So some other, you can recognize some of these. This one you won't recognize unless you've done your botany. This is a thing. This is a division of the plant kingdom. There are 12 divisions roughly. This is called Genetophida. It's a weird plant, but it grows in Africa. But you recognize roses, flowering plants. Well, this is a sundew, a flowering plant, but it's carnivorous. They don't have it in the Met-How, but they're nearby. They're in Swamp Creek. Flowering plant, flowering plant. Okay, this is a ginkgo. There are 12 divisions of the 12 divisions of plants in the plant kingdom. One of them is ginkgos. Guess how many ginkgos there are on the planet? There's one species of ginkgo, but it's a living fossil. There used to be many ginkgos, and now there's only one. So we don't have time to deal with the evolution of the plant kingdom, but there you have it, the plant kingdom. But these are all photosynthesizers. These are pumping the other 50% of the oxygen into the atmosphere that other life needs to exist. If you're going to put together complex chemicals from the original sugars made by photosynthesis, like lignin, which is wood, you're going to have to take it back apart, or you're going to run out of the elements necessary for life. And that's the function of the kingdom of fungi. I wanted to mention with the plant kingdom, there are about 300,000 known plants. There are about 150,000 known fungi, but fungi are harder to count. Many fungi are microscopic and live in the soil, so there's probably many more than 150,000. But fungi are the decomposers. I put fungi, for fun. And many people say fungi, your choice. But they take apart the complex chemical structures made by the plant kingdom and other kingdoms. But the interesting thing is, where did they come from? This is called a cladogram. It shows evolutionary relationships. The closest evolutionary relationship to fungi are animals. Put a circle around it. So if, in terms of our relationship to the rest of life, we're most closely related to fungi. No offense. Animals. So there's up to 30 million. We can't count them. There's too many because most of them are tiny or insects. But out of the 1.5 million that have been counted and have scientific names, 1.5 million animals counted, about 30% of them are beetles. And I may have said this before, but one biologist was asked by a minister, what have you learned about God from your study of biology? And JBS Haldane, the biologist, said, God has an inordinate fondness for beetles. There's so many beetles on the planet. Okay, life has increased over time. These are gigatons, billions of tons. There were no gigatons on the early planet. Then there was just bacteria, which actually weighs in pretty heavily here. Nobody's weighed it. It's a hypothesis. Archaea up here. Look at viruses. There's a lot of viruses, but they don't weigh anything, so they barely show up. In any case, this is the total weight of life on the planet. It's an emergent property of the evolutionary journey because there was none of it, and now there's 600 billion tons. There's 600 billion tons of life on the planet. Here's another picture of the same thing. There's 100 billion more made every year from the process of photosynthesis, and the number doesn't go up. Why? Because fungi and bacteria are decomposers, and life only lives so long. And composers, first they compose and then they decompose. Wow. So what dominates the biosphere? Plants. Why? Because they're the only things that can make their own food. We're dependent. All the other ones are dependent. I mean, that's not strictly true because algae and cyanobacteria, but they're not major players. Most of the life on the planet are trees. So we're at the end of the journey, but we're on this evolutionary journey. We have a fish coming out of the water. This is what it's concerned about. Eat, survive, reproduce. Amphibian turning into a reptile, turning into a primate. Eat, survive, reproduce. The question is this character something different in the evolutionary journey, or is it not? So I'm watching for the third time this 48 lecture series by David Christian, which, as I said, I'll give you if you give me a flash drive. It's quite good. And he makes a case, Homo sapiens is something different. And if nothing else, our all life, life eats. Why does it eat? It needs the energy. It needs the energy captured, the energy coming from the sun, captured by photosynthesis to maintain a internal environment that's different from the external environment. Homo sapiens has commandeered something like 40% of all the photosynthetic energy captured by plants on the planet. That means we've taken all that away from the other organisms. How else does he say that? The human body needs 2,000 calories, roughly speaking, 2,000 calories a day to maintain its internal environment. Humans now use about 250,000 calories a day because of our use of fossil fuels. There's no other organism that in any way compares to our command of energy on the planet. And as David Christian points out, we have the capacity for symbolic thought, turning the external world into concepts in our head. And as I like to say, all thought is symbolic. If anybody can have a thought that is not symbolic, show it to me. But that allows us, I mean, it actually does a lot of damage, but it also allows us to interpret the world we live in and gain some understanding of the world and to share information across the generations, collective learning. We can tell it in stories, we can write it in books. The other animals are not writing books and passing on acquired knowledge to future generations. So there is something different about Homo sapiens. You know, we're having a tremendous impact on the planet, but we're an evolutionary process with tremendous potential. Just to briefly mention viruses, because they deserve mention in the way that I already mentioned. They are the strangest little creations. They have no life of their own. All they have is DNA inside a capsule. It doesn't even rate as a cell. It's some kind of chemical capsule, but they have an electromagnetic attraction to their prey. Fortunately, mostly bacteria. They mostly prey on bacteria, but there are unknown numbers of virus types, and some of them prey on us. This we know. Size of viruses. So I circled a couple of. So nanometers. Let's see. A nanometer is a billionth of a meter. So viruses, bacteriophage. A bacteriophage is a virus that eats bacteria. That's what most bacteria do. I'm reiterating that. They're tiny. Viruses are only about 100 times larger than atoms. And we didn't know they existed until rather recently. And now, oh my gosh, I forget the actual number. I wonder if I can find it here. I can. It says in a teaspoon of seawater, there's 100 billion virus particles in a teaspoon of seawater. That's unimaginable. What are they doing? They're eating bacteria. They're bacteriophages. I mean, it's like that quote. I may have said it before, and I was supposed to come up earlier here, but a Unitarian minister said a few years ago, he said, the fundamentalists are upset that we're related to monkeys. He says, the scientific study of DNA shows us that we're related to zucchini. So get used to it. It's a community of life, and we are a community of life, and we're just learning this, and it's a beautiful, beautiful thing that Homo sapiens is figuring this out, and we don't know where it'll take us, but I think the potential for us to live on the planet as stewards is high. We certainly have not arrived there, but look at the journey that we've been on is very complex. This is just a wonderful picture. I think it's the last slide. And we have that famous quote by, this is the last sentence, this is only part of the last sentence in Charles Darwin's book, The Origin of Species, on the origin of species. There's grandeur. He's talking about evolution. You know, that's a wonderful picture of evolution there. Grandeur in this view of life, having been originally breathed into a few forms or only one, that while the planet has gone cycling according to the fixed laws of gravity, from so simple a beginning, endless forms, most beautiful and wonderful, have been and are being evolved. So that's the journey of the universe, you know, the evolutionary journey of life. It's totally mystifying and beautiful and catastrophic in its